All right, so what's due on Monday? Yeah, so we got both the Connect and Excel assignment. When I get back from teaching today, I think I am going to push that Connect due date up to Wednesday. So I'll give you a little bit of stagger. So if you want to kind of focus on that Excel assignment first, then you'll have a couple days after that to kind of finish the Connect. So that change should happen this afternoon. Don't forget, however, there's a Learn Smart that also needs to be done before we meet in class on Wednesday, right? Should just be an easy 10 minutes kind of walk through, kind of get us primed for the next topic we're going to start talking about next week, which is probability. Other than that, I don't think any other housekeeping stuff from me. Are there any questions from me before we kind of jump into material today? Okay, so today we've kind of been going through. Similar when we were looking at graphs, we went through a bunch of stuff, and I said, okay, we've only been looking at one variable. What about the relationship between two variables? So we looked at scatter plots. We'll kind of do that today, right? We've been doing descriptive statistics for one variable, right? The mean of one variable, the variance. Today we're going to focus on measures of relationships between two variables, okay? So if we're thinking about this, a lot of times we're interested is one thing changes, right? As this X variable, whatever it happens to be, goes up, what happens to this other Y variable? Like, does it go up? Does it go down? Or does it not really change much, right? So as X goes up, does Y tend to also go up? Do we see a positive relationship between these two things? As X goes up, does Y tend to go down? Do we see a negative relationship? Or as X goes up, does Y not really change? That would be kind of no relationship. So we've got two measures, which are the covariance and the correlation, or sometimes called the correlation coefficient. Okay. So kind of similar to like the standard deviation, we kind of first need to calculate the variance. In order to come up with the correlation, we first have to know how to calculate the covariance, right? So the correlation or the correlation coefficient uses the covariance. So we'll talk about that one first. Right? And we can calculate a covariance for a population or a sample, just like we did a regular variance, right? But it's a little bit different, right? So they have a similar name, but we're really measuring something. Well, let's see that there's a reason why we might have that variance word within here, but it's a little bit different. So let's just look at the equation for the population. I'll kind of break it down. We'll go through some examples to see what it looks like with some numerical values. But basically, right, we're going to go through, we're going to call the covariance sigma, kind of like, we'll use sigma for the variance into the standard deviation. But instead of just one subscript, when we use two, right, X and Y, here are two variables, that's going to tell us, okay, this is actually a covariance. So sigma with two variables subscripted, that represents a covariance. What we're going to do is go through every single observation. Right? And we're going to look at the two variables X and Y we're interested in. For the first observation, we'll look at what value does it have for that X variable, and we'll look at that difference from that value and the mean, right? So we're subtracting the mean from that X value. We then look at that same observations value for the Y variable and find the difference between that Y value and the mean of the Y variable. So this would be something like, let's say the average number of years of education is 14. And the average income is, I don't know, 45,000, right? So I see somebody who has 12 years of education. So the first person has 12 years of education. I would then subtract the average education, which I said was 14 years. I would then take that difference and multiply it by that person's income, which I think I said was 45, or I didn't say that. Let's say the person makes $60,000. So I would take their income of $60,000 and then subtract the average income of $45,000. I would then multiply those two differences, write that number down. I then go through and do that for every single observation. And remember that summation sign tells us, then add them all up. So, and then we divide by the total number of observations. And I'll kind of dive into that a little more here in a second. So what does this numerator really measure, right? We think about, we just look at it, what it's going to try to pick up is whether or not there's a positive or negative relationship between the X and Y variables. So eventually, when we calculate this thing, we're going to have three kind of different ranges. One is it's positive. That tells us that overall, the observations give us represent that there's a positive relationship between these two variables. If we get a negative covariance, it says across all the observations, it appears that these two variables have a negative relationship, or that as one goes up, the other tends to go down. And then if it's zero, it means there's pretty much no relationship. As x goes up or down, y doesn't change at all. Now, the way we're capturing this relationship, being positive or negative or zero, is really coming from the fact that we're thinking about, do these variables tend to be on the same side of the average? Right? Because if the x and y variable, let's say I have a person and they were above average income and above average years of education. Well, then when I subtract the average, I'm going to have a positive value times a positive value. So that was an observation that provided evidence that these two things tend to be on the same side of the average. Let's say I had someone below average education and below average income. Well, when I subtract the mean from both of those, I'll have two negative values. A negative times a negative is a positive. So if they're both below the mean, I still add a positive value to that covariance, because if both things are low, that's evidence of a positive relationship. They both tend to be on the same side of the average. If x is low, y tends to be low as well. If x is high, y tends to be high. Right? There's this positive direct relationship between those two. Now, for every observation that would be evidence that there's a negative relationship, that would mean that when one of them is above average, the other tends to be below its average. So, if I tend to, let's think of someone who's above average years of education, but below average income. Well, being above the average education, I'll get a positive difference multiplied by being below average income is a negative difference. So positive times negative. That observation would add a negative value to the covariance, because it was evidence that these two variables tend to be on different sides of the average. So it's kind of the intuition behind what the covariance is picking up. And then when we divide by n, it's kind of like when we're doing the mean. It almost like weights everything equally, right? Every observation carries the same weight. And then if we had sample data, just like we did with the variance, we had to divide by n minus 1. Right? So it still kind of follows that same rule that we're using for the variance, which is for a population I divide by n, for sample I divide by n minus 1. Okay? So some actual values might make sense how we actually work through this a little bit easier. So let's say I had this data set, 44,000 people. I've got all these heights and weights, right? And then I might think about, probably ahead of time, I could probably guess that the covariance between height and weight would be what? Positive, negative, or zero? You would take a guess, probably positive, right? As people are taller, they just tend, all things equal, they tend to weigh, right? You got more bones and organs, I don't know. But so, well, not more organs, but like more of the same ones, right? So we've got this first individual. We can compare their height and weight to the averages, right? So I have the averages down here. Tend to do a little bit. I think this might have been something about this had more females in it, but we had 64 inches pretty much was the average height, and 187 was the average weight. So if we look at this first individual, if we subtracted the mean height from their height, well, they're above the average height, so we get a positive value. Right? And they're quite a bit above the average height. However, when we look at their weight, they're actually below average weight, right? 179 is less than 187, so they're below. So this is evidence that at least this one person, that height and weight tend to be on different sides of the average, right? Or that there's a negative relationship between the two. And we kind of get that by when we take that positive difference for the x variable, the negative difference for the y variable, and multiply them together with this negative value. But that's just one observation, right? So that goes against our intuition, but for any one person, the relationship between two variables doesn't have to hold. I can tell you there's a positive covariance between years of education and income, but when you're looking at, choose your billionaire high school or college dropout, right? It's not going to apply. However, if we go across every observation, right, we look at the next two, these two people were, one just barely, but they're below average height and they're below average weight. In fact, all three of these people are below average height and below average weight. All three of those observations are evidence that these two variables tend to be on the same side of the average, right? So when I take those negative difference times negative difference, all three of those observations add a positive value to the covariance. Because they were three observations that provided evidence that these two variables tend to be on the same side of the average. Now you'll notice, like this one right here, because the person was, significantly below average weight, right? They added it was evidence of a really strong positive relationship to height and weight. Whereas when we have somebody who's just barely below the average height, that added a very small, because that, even though it was evidence that they tend to be on the same side of the average, it wasn't strong evidence, right? So you can imagine we could go through and do this for every single person, and what we're really picking up is almost like when we add all these up and divide by the total number of observations. Excuse me. What we're really picking up is like the average evidence across all observations of whether or not these two variables are on the same side of the average. That's really what we're picking up in probably the least textbook definitional way of saying, right? But that's probably the intuitive best way to say, which is sad those two things are not. But right, so we went through and did this for this whole data set. I think we ended up getting 76. I had this data set later on my computer, so I went through and I found the covariance. Right? So the covariance between height and weight is 76. Right? Well, what the hell do I do with that? Right? What does that mean? Is that high? Is that low? I mean, part of the problem with the covariance we're going to find out is, first we want to think about what's its units. Right? So my x variable of height was in inches, and my y variable of weight was in pounds. So what are the units here? Well, I'm multiplying inches by pounds, so I've got inch pounds. I don't know what that is, right? Years of education and income, I would have years times dollars. My units would be year dollars. Like that doesn't mean anything to us, right? Furthermore, I can't compare the relationship between height and weight to years of education and income because they're completely different units. And just the variable of income itself, I mean, I have much more variation in income. I see incomes that range from 0 to the millions. Well, as height, I'm going to see, I don't know, take the shortest and the tallest person in the world. Maybe you're talking, I don't know, 50, 60, max 60 inches, right? And that's of all the humans that have ever existed. So we've got a units problem, right? And we know that the covariance will be influenced by the original variation. I said it in terms of the range of the data, right? That's one measure of variation. But it'll be influenced by the variation that exists in whatever two variables I'm looking at. So what can I do? Right? So we're actually going to scale the covariance and create another statistic called the correlation coefficient, which is much more useful for us. And I'll give somewhat of an insight as to like how we do this. I'm not going to like give the exact mathematical proof, but I think I'll show you enough that I'll convince you that this procedure for calculating the correlation coefficient will give us something that's scaled, and then we can compare across different types of relationships. Excuse me. So all we're going to do is go through and take that covariance between those two variables and divide it by the standard deviation of each variable. Right? So if it's population, right, I'm just writing this notation out for the population. We call that correlation coefficient rho. If it's for a sample, we call it R, and we're kind of using the sample versus population notation. First of all, before we kind of keep going, I pause and ask, what kind of the procedure of how we calculate the covariance? Any questions on that? Okay with this? So one of the reasons I'm pushing the Connect assignment up to Wednesday is because the last like 2 or 3 questions kind of deal with some of this. All right. So what we end up with, if we divide this covariance by the standard deviation of the variable, is our correlation coefficient will always be between 1 and -1. Same kind of idea, right? The sign of our correlation coefficient tells us the direction of the relationship, but then how close it is to 1 or -1 tells me the strength. So a positive one would be the strongest positive relationship that could exist between two variables. -1 is the strongest negative relationship that could exist. And then 0 still represents that there's no relationship. Now you'll notice, I mean, if I look at the equation for the correlation coefficient, what's true about my standard deviation? I think I didn't say it specifically, but we said that there's something about the variance that we know it always has to be greater than one value. So the lowest value of the variance could be was what? Data set with no variation would have a variance of 0. And we said that's the lowest it can be, and that the variance always is going to be positive because we're squaring all the deviations, right? So we know this, my variance is positive, and I take the square root of it, I'm always going to have a positive standard deviation as well. I can never see a negative variance or a negative standard deviation. So the standard deviations are always going to be positive. The sign of my covariance tells me the sign of the correlation coefficient. Because I'm just dividing it by two positive values, so the sign will stay the same. So let's think about why dividing by the standard deviation is going to scale it to be between 1 and -1. And when we're dividing by the standard deviation, I kind of said the covariance is going to be dictated by how much variation exists in the original x and y variable. So if we divide by the standard deviation, intuitively what we're doing is we're trying to like account for that original variation that existed in the variable, so that we are scaling the covariance, so that when we divide by each standard deviation of each variable, it's almost like we're saying we're starting out with two variables that have the exact same variation, right? Now we can maybe compare a cross relationship. So what does this get for us? So let's write this out. So we've got, actually, I'm going to keep this in terms of the population real quick, and I'll get out of the way. All right, so here's my equation for the covariance. All right, just writing out that numerator, what that covariance equation is. And then dividing by the standard deviation of each variable. So square root of the sum of the deviation squared divided by x, right? And then multiply that by the standard deviation for y, which if I write that out, end up with something like this. So I just plugged in my equation for the covariance and the standard deviations, and we can start to think about why this kind of scales it between 1 and -1. So if we look at this, first of all, if I've got the square root of n times the square root of n, that just becomes n, right? So you can almost think about here, I could rewrite this as, and you're not going to have to like do this proof, I'm just kind of showing it to you for completion's sake, and so you don't just think I'm making things up. So, or sorry, they're both divided by n. Square root of n times the square root of n is just n. Well, now my numerator and denominator have the same thing, so that cancels. And you can now kind of see, okay, well, I've got the square root of something squared. That's kind of going to cancel. I can't exactly do that with a law of summations, but that's the idea. And then notice I've got the sum of the deviation for the x variable and the sum of the deviation for the y variable. You can kind of see how things would cancel to be 1, right? But like I said, taking the square root of the summation of something squared, it doesn't exactly cancel. And that's why we still end up with not always 1, but something between 0 and 1. Or not always -1, but something between 0 and negative. So dividing by the standard deviations is really what kind of scales this down, accounting for the original variation of data. This is like a half mathematical proof, like it wasn't a complete or by all means completely accurate, but it kind of shows you, you can kind of see the things that would cancel, right? To get the intuition behind why. So if we had values for these variables, I mean, this becomes very easy. Once I have my covariance, the correlation coefficient should be very easy to calculate, right? So let's say I go back to that data, I find the standard deviation in height and the standard deviation in weight. I've got my covariance of 76. All I'm doing is plugging my values into that correlation coefficient equation, and it's pretty simple to enter that into our calculator. So we get this correlation coefficient of 0.45. Well, if it ranges between 1 and -1, what could we, I mean, you may not know exactly what represents a strong or negative or a strong or weak relationship. But here, if the maximum value I could see is 1 and no relationship is 0, 0.45 is kind of like middle of the road, right? It's not the strongest relationship, but it's definitely not the weakest, right? So usually I'm really looking for a strong positive correlation. We like to see things like 0.8, 0.9, like quite a bit higher. But by no means is this evidence that there's almost no relationship, right? You can't look at me and say there's no relationship between height and weight. That would have to be a correlation of, closer to 0, so something like 0.1 or 0.05. So we have, evidence that there is a relationship, but it's not like the strongest, right? But the one nice thing this does is it now gives us a value we can compare to other relationships, right? So I've got height and weight right here is 0.45, right? It's positive. So let's say that I'm then thinking about, now I write this out in terms of a sample. I've got the correlation coefficient between exam scores and the hours of Netflix watch. Right? If I told you that there's a negative relationship between the hours of Netflix watch and your exam scores, right? And then that relationship is stronger than the positive relationship that exists between height and weight, what are some values, or what is the range of values that I can see here for the correlation coefficient? So it's a stronger negative relationship than the positive relationship that exists between height and weight. So the range of values I can see for would be so negative. So if it was, let's think about this. If it was negative 0.3, right? It's a negative relationship, so the negative sign of that. But if it's 0.3, it's actually going to be closer to 0 than this one would be. So it would actually be evidence of a weaker relationship. So instead of being something like negative 0.3, it would be negative 0.57, anything above 0.45, right? Even if this was, negative 0.46, it's a stronger negative relationship than the positive relationship that exists in height and weight. So it's kind of, we have to be careful when you go negative, you actually think a stronger relationship is actually closer to -1, right? On either side, a stronger relationship is moving further away from 0, right? So the positive relationship closer to 1, the negative relationship closer to -1. And I think I put up those sample questions. I think there's a question on there that talks about 2 different types of relationships and thinking about what are potential of these 4 answers, which one of them could be. And given what you were told about the positive negative relationship and how weak or strong one was relative to another, what are some values that would fit that description, right? And this, we can do that because we've scaled that covariance, right? So now that there's no units, you can think about when we were dividing everything, right? We had inches, pounds, units cancel. So we've got a nice unitless measure that allows us to compare across different types of variables relationships. Okay? All right. Any questions on that? All right. So, this isn't exactly what we're doing. We'll kind of see towards the end of the course. But for the sake of where we're at right now, think about this correlation coefficient. When we were talking about scatter plots, right? What did I have here? I guess I put the height and weight on here. You can kind of visually see there's a positive relationship, right, between these 2 variables. If I had to draw a line that went through the middle of this data or best fit the data, it's probably upward sloping, right? Its slope is probably positive, right? So, if you ask me a question like this, honestly, this is almost too easy, right? But just so that we're getting the idea of how we calculate this down. If I had 21,000 kids and I find that, I think I had birth, I think if I remember right, this was birth weight and length of the pregnancy. Or maybe I flip-flop those, length of pregnancy and birth weight. But the covariance was 330. I've got the 2 standard deviations for each variable. What would the correlation coefficient be? So here, what are 2 answers we could rule out right away? Well, one answer should be pretty obvious we can rule out right away. Why? It's outside the range of 1 and -1, right? So it doesn't make any sense. It could be our covariance, can't be our correlation coefficient. What's another one that we can rule out by looking at the values for the covariance and standard deviation? Yeah, because it's D, because it's negative. And why can't it be negative? They're all positive, but also remembering the sign of the covariance is the same as the sign of the correlation coefficient, right? So if we have a positive covariance, we know that the correlation coefficient will be positive as well. So negative answers make sense. The only 2 that we should even be, just taking a stab at, we can already narrow it down to just a 50-50 shot now, right? It's going to be one of those 2 answers, A or C. I think it ends up being A if you do the actual math. Right? I put up another example here. It's just different numbers. You can kind of think about the same principles apply. Here, which one can we rule out right away? Not as obvious, but it's still out the same reason, right? 1.2 is outside the range of 1 and -1. Right? And then once again, I can also rule out D, because even though it's really small, my covariance is positive, so I know my correlation has to be positive as well. So this would be like a really easy question, so that's why I'm kind of going through them quick. You can divide a number by 2 other numbers. So it's more of like we hear about like the interpretation of what this correlation coefficient tells us. So I think I'll save this for the end. It's like a 3-minute video. It's kind of funny, but we'll like introduce the idea of probability just a little bit ahead to start next week. Save us a little bit of class time. Maybe get out earlier, a couple classes next week, as well as probably today. So you guys are ahead of the other section because they lost out on Monday, and I'm not trying to be all over the place. So you guys get a little bit more time. So lucky. All right. So the next topic we're going to jump into is, well, let's just stick with correlations and covariances, and I'll actually show you some stuff in Excel that might be helpful. Let's go here, and I think I want to use where would I have 2 variables? I think it's in, let's see what this looks like. That one's not very interesting. Is this the drug one I think I have? Yeah, okay, this one's a little bit more interesting. So, let's do the correlation between this and I think this is number of, there we go. So I'm going to, so one thing I'll show you, it's kind of helpful in Excel as we start to work through some more of these, and it's not necessarily going to help you like solve a lot of the problems. It's just going to be a pretty helpful feature to get a quick idea of the data, right? So I have these 2 variables. Hopefully these aren't all ones. As I said, I think I got 1s and 0s in here. So I've got the number of convictions and kind of marijuana use, right? It's kind of a weird variable because the number of convictions is discrete, but you'll get the idea about kind of how we would find these covariances. So one thing I can do real quick is if I hold Control and Shift or Command Shift on a Mac and use my arrows, I can select the entire data set pretty quickly. And then I'm going to go up to this data tab and click this filter button. So what this filter button does, kind of show you up here. So it adds these little arrows there, which then allows me to do things like sort the data from smallest to largest. Right? Sort the data from, 21 convictions, from largest to smallest, right? I can kind of get an idea about what this data looks like. Okay. So, how would I find the covariance? So there are built-in functions into Excel, kind of that covariance.p, covariance.s, which tells me either the sample or the population covariance. So I'm going to do this in a cell that's way over here for a second. We'll treat this as though it's sample data because it is sample data. It's only, it's not the entire population. So all I'm going to do is select my 2 variables. So for the first array, that's my first variable. So I'll do number of convictions. So Control Shift or Command Shift on a Mac, hit the down arrow, right? Where's my home key on here? That's not going to work. All right, so I think I accidentally just put a 7 in there. So I selected, I've got 11,000 observations. I'll put a comma, and then it wants me to tell it the second variable, right? I'm looking for the covariance between 2 variables, so I've got to select 2 of them. So then go to my second variable, Control Shift or Command Shift, hit the down arrow, hit Enter, and I can find, I've got this covariance of 2. Right? I could also do something like,
standard deviation of convictions, and then we'll do standard deviation of marijuana use. Right? And we've already talked, so stdv.s, right, my sample standard deviation. I'll select my first variable, which is the number of convictions, and then stdev.s, the sample standard deviation of this marijuana use variable, right? And now I've got the three things I need to find my correlation coefficient, right? So all I have to do is take my covariance, divide it by, we're putting it in parentheses, that standard deviation of convictions multiplied by, I think it's in cell H3, that standard deviation of marijuana use. So that should give me my correlation coefficient of 0.17, right? So pretty low, right? You're coming at me and telling me that using marijuana is causing people to go to jail. I mean, by the letter of the law, that it will, but it doesn't influence the number of convictions very strongly at all. I mean, much lower than we had the relationship between height and weight. Right? I could have also done choral, right? So same kind of idea. I select my first variable, this built-in function choral, not like the C thing, and then marijuana use, right? Should give me the same value. Right? Just like the covariance, we're just calculating, it calculates a standard deviation behind the scenes for us and then spits out at us the correlation coefficient. Now we could have also done this by hand, right? And it honestly, I mean, wasn't a built-in function, but it would help us see the intermediate steps and also like not take a whole lot of work. So I'm going to create two columns. One where I take, oops, the X values and subtract the mean, and one where I take the Y values and subtract the mean. So equal sign, well, actually, I guess first I would then have to calculate the mean, right? So let me put the mean of X and the mean of Y over here. What function do I use to find those? Find the mean, the function in Excel is the word I said we don't want to use, but average, right? Yeah, I didn't program it. So we'll select our first variable, find the average. We'll then find the average or the mean of our second variable. Once again, I'm doing this so quickly by using that Control Shift, Command Shift, and hitting the down arrow. So now I've got my means. I'll say, okay, take the value for X and subtract the mean of X. But I want to be able to copy this down real fast for every single observation, but what's going to be the problem? Huh? Yep. The cell reference for my mean is going to update, and I'm going to start moving down to cells that have nothing in them. So I need to make sure that, yes, I want the value for the X variable to update when I copy this down, but I don't want that mean cell reference to ever change. It's always going to be using that mean value. Questions on anything up to this point? Okay with all this so far? Honestly, a lot of this stuff we've already done, but so then to do this really quickly, if I move my mouse over to this bottom right corner, if I double left click when it shows up with this bolded positive sign, it does this for every single observation. Right? So now the reason why a lot of these values are the same is because the Y value, or sorry, the X value here is the exact same, right? So it should be the same deviation from the mean if it's the same X value. And it's because I have them sorted that they're all showing up next to each other. I could then do the same thing for the Y variable. So take the value for the Y variable, subtract the mean for that Y variable. But I don't want that mean to change when I copy it. So I freeze that cell reference. Copy this down, right? And now I've got kind of these two columns. I could then basically take, so I want X minus the mean of X times Y minus the mean of Y, right? Create this new column. It's just going to say, take this value, multiply it by this value. Right? That's all that is. Now I can copy this down real quick, double left click. I then want to add all those values up, right? Across every single observation. and then divide by the total number of observations I have. So I didn't do this ahead of time, and this is an example where I can use multiple functions in the same cell. So if I added up all those products, right, I've got my numerator. What was in the denominator if we had a sample was just the sample size minus 1 or n minus 1. How can I find, or the total number of observations? How can I find the number of observations? There was a function I mentioned last week in Excel we can use. Does anybody remember? It's pretty easy. So if I want to count the number of observations, there's actually a count function. I think we used this at one point to check to make sure when our frequencies added up to 50, right, or the total number of observations, we could also use the count function to double check that's the same number. So that count function is just going to go through and count the number of observations that have a value in them. So I'll select either variable here, it wouldn't matter which one. I'll have the same number of observations. And then I have to add in minus 1 here. So I'm going to put a parenthesis, minus 1, right, and make sure I'm dividing by n minus 1. Okay. Hopefully, I get the same thing that I had over here. Or, nope, yeah, right here. 2.0175, right? So that's my covariance. And then I can go through, divide the covariance by the standard deviation. And that's a much longer way to do it, but it kind of breaks it down to steps. And I don't know, it was kind of a way for me to kind of show you some of this filter, you know, how to filter it. I don't know, just another way of kind of seeing how you would do this in Excel. Okay. Any questions over anything there? I'll probably save this. I'll post this not as probability tables. I'll put this up on Canvas that kind of has some of this work. Call it covariance or something like that. So I'll save that right now, actually. Let's call this covariance example. And that'll be up there for you. So you can kind of go back and look at it if you need to. All right. We've got 13 minutes. So first things first, for those of you who showed up, I guess the question here, it doesn't really matter what you answer. I'll just kind of give everyone credit if I can get this to start. Maybe. What's happening? Let's try reopening this. Let's see if that helps. No. Yeah, if it doesn't work, it doesn't work. Let's see if this will play. All right. There we go. So just respond with, I don't know, whatever letter makes you happy today. I know, just so I can get your names recorded, basically. And then we'll watch this and have a small discussion about it after it's over. It's not very long. So there's 25 of us here, 26. Everybody had time to get it in? The answer in? All right. Oh, 27. All right, we'll close it out. So, where did it go? There it is. After this ad, I'll turn it up. Play this right before lunch, right? All right, we get it.
Candidates finally waded into the foreign policy. We've made great strides in eradicating prejudice in this country.
But according to the University of Texas,
Supposed to be somewhat complicated.
one part of society
Fine.
is still suffering.
Ugly people. They're bad looking, wind up with a spouse who's not as good looking, and people are less happy.
Are you currently happy?
Yeah, I'm a very happy person.
Okay. He's got a mountain of hard data that shows how these people are being left behind.
You know that they'll have more trouble getting loans, and they do get loans, but get loans when the kid turns on.
Good. And you know all this because you are
An economist. No, an economist. I'm a professor of economics who's done a lot of research on this.
okay.
I would think I'm average.
So as a cold, hard, factual number, you would consider yourself a 3 out of 10.
I would be a 3 out of 5.
3 out of 5. Unfortunately, Hammermesh sees discriminatory barriers almost everywhere he looks.
Ugly people make less money than otherwise identical good-looking people. Maybe 230,000 over a lifetime compared to a good-looking person.
Have you been to the offices in Google?
No, I've never been.
It's like that space cantina in Mos Eisley from Star Wars.
Well, like I said,
Do you know how rich those ugly son of bitches are? They are filthy rich. And yeah, they all look like Walrus Man.
they're better looking than one other thing.
They work at Google. Google. So if Anglo-Americans are hurting, what can we do for them?
We could extend legal protections to help ugly people, just as we do now for racial minorities, ethnic minorities, women, disabled individuals.
So you're saying, let's say a quadriplegic is in the same category as a bad-looking American.
To me, these things are both equally non-amelioratable, can't be fixed. Why then, to me, they might well be viewed being the same group.
But would those groups be willing to share a piece of the social justice pie? I sat down with advocates representing African Americans, Native Americans, women, the gay and lesbian community, and the disabled to find out.
Having a significant disability like quadriplegia impacts every major life domain, from housing, recreation, employment.
But when ugly people walk down the street, they get funny looks.
Of course, they are walking down the street, which is not something most quadriplegics can do.
Which brings me to my next point. There are no assistive devices for ugly people. They all found reasons to put themselves ahead of ugly.
All the communities that are represented in LGBT rights and disabled women suffer disproportionately. We know that.
I'm against it. But you have to have some priorities. If you're a society, if you're a government, if you're a company.
And what is the marker for an ugly person? How do you define an ugly person?
This guy,
I think that this is a person that is ugly.
he rates himself a 3 out of 5. Can any of you imagine the pain of what it's like to be 3 bits of a person?
Oh, I'm not answering.
Exactly. Because you can't think of it.
No, that's not good at all.
Despite the rejection, Hammermesh remains unbowed in his fight for justice.
You have to be able to quantify beauty, okay? So I started walking around campus, looking at everybody and giving them a grade 5, 4, 3, 2, 1.
That's not creepy at all. Creepy or not, it was sound science, and I joined him in his laboratory. Come on, that's 3 5s.
No way.
What?
3 and 2 4s if you're being generous, sir.
We carefully collected data, and it quickly became clear that this seasoned economist was better with numbers. I got a 5, a 5, and a 4.8. What do you got?
I'm a tough guy. I'd say 2 3s and a 4.
Fuck off. And as he continued his research and his fight for justice, I realized the pie might be big enough for more than just the ugly.
So then it goes off the rails a little bit, but no, it's meant to be funny, but at the same time, it's kind of interesting. That guy's actually really smart, believe it or not. Well, like economists are bizarre individuals. So there's a bunch of research out there that looks at this, and really ultimately what we're trying to do most of the time is it's a little more complicated, but essentially it's finding that correlation coefficient, finding something, the relationship that exists between 2 variables. So one study they did, he specifically did, was they created all these resumes, right? And they had the exact same resume and they sent it to the exact same companies. But it was through LinkedIn, so they somehow had a picture associated with it ahead of time. So they were using fake pictures as well. And ahead of time, they had, however many, couple hundred students they could get, rank people and put them in percentile, like basically rank
their attractiveness, and then put them in percentiles, right? So what they found was these photos they were using on LinkedIn that were rated as being in the higher percentiles actually ended up with higher numbers of interview requests, even though they had the exact same resume, right? And they broke it out between gender. You can obviously see this is much more disparaging for women than it is for men, right? So it's kind of being able to understand the relationship between these two variables, something like this, gives us a lot of power to identify, like, hey, we have a problem. This is not a good thing, right? It doesn't tell me at all how you can perform the job. In fact, based off your resume, there was no reason I was led to believe that you like either of these people could do anything different, right? They looked like the exact same person when it came to their actual skills. So kind of funny, I like the old John Daly stuff, but it is actually have some pretty bad implications. Actually, that guy did find some relationship between these two things, and I would argue you probably don't want this on our society. So I'm gonna end on that. We will pick up on Monday, starting probability. That Learn Smart, that's not due before class. So Wednesday will really be about the harder stuff for probability. So have a good weekend. I'll see you guys on Monday.